Alright, so what we're going to be doing in this video is we're going to be using Desmos to help us examine the actual graphs of each of the thrill ride proposals. We have our estimates, and I should have estimated the two I didn't demonstrate for you, and even that third one, which I told you I didn't think was correct. And we're going to go ahead and jump over. So when we do this, you're going to sketch an actual graph, and you're going to talk about what you got right and what you missed. So here we go over to Desmos, our good friend. And so I've already typed them all in. So I'm just going to start with the first one. And it's hard to see in this window. That's the other thing it talks about, is some features obscure others. So let's kind of zoom it in and out. Let's see what we got here. And it does seem to wave and go up. And I just also graphed what 2x here. You'll notice it's following the path of 2x as it waves and goes. It's not really like a perfect equal distance on each side, but it kind of is. And so that's what's happening. If I go back to standard, you can kind of see it a little better. And you're going to want to pause the video now or do your own one Desmos and sketch in that graph. Okay, so with that one in mind, let's do the next one. And I'm going to take it back to a standard zoom. And I'm going to get rid of both of those because I don't need them. And this has an amplitude of 10, so the height looks good. I'm going to spread it out a little. Well, let's just keep it here, 10 and 10. Let's see what happens. Okay, so it's turning around here and here. So I also graphed the one without the absolute value on it. You can see it's going down, and so everything that was under the x-axis has been flipped over and changed. So let's turn this back off because that's what the absolute value does. I hope you figured that one out. If we zoom, if we go a little bit, let's change our window here so that our x-axis goes maybe just to 4 pi. So 4 times 3 is about 12-ish, 12.7 we'll go with. And so you can see this would be from to here, which is 2 pi. That would be a normal period, and for us that's 2 bumps. And then there's another 2 bumps. So that's kind of the idea. 3 pi, pi. Okay, pi halves at the peaks. So go ahead and sketch this one in and see what you think. Again, pausing the video so you have a chance to do so. Or you don't have to pause it while I clean it up. Get ready for the next one. Alright, so the next one, we're going to go back to our standard window. We're going to move it here. And this was the one called the amplifier, if you recall. And I didn't do anything else. So I've got this. It looks a little funky, so we're going to, first of all, we're going to go like that and kind of see it on both sides. So we don't really care about the negatives, but it is interesting that the negatives are just a reflection across the y-axis. But see how it's getting larger or amplifying the volume? This would be what your speaker does to sound as it comes in. But it keeps getting larger and larger as you go from left to right. So my peak here, my peak down there, and we'll get. Okay, so I don't remember what I was saying when there was a knock on the door, and then it's been a couple of minutes, a little while. But so we have this graph with the amplifier. I just wanted to show you some key points. Here we have pi, then 2 pi, 3 pi, 4 pi. So it is still crossing the x-axis in the same places because the period didn't change, but it's that amplifying, called the amplifier, is causing it to bounce high, 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 high. And like we honestly, even to actually see what's going on and to see how high it's getting is really hard. That's 30, almost 40, and so on. So it gets pretty high pretty fast, but that's the idea behind the amplifier. So the next one was called the periodic bump, and I'm going to just go back. No, not the periodic bump. The next one's called the gentle wave. And so that would be the one with the exponential graph. And so going here, it starts out getting all the way up almost to 10. Not quite on this whole peak, but it's at 8.5. We've got pi and 2 pi. But see how it's getting lower, and that's the exponential decay model, making it kind of taper off into nothing. Never quite gets to nothing. Like if we zoom back in over here, it's still bouncing around. But like this peak is not even, I mean, 0.8 is really, really small. So, and over here on the other side, it kind of does what the amplifier was doing, except for it's tapering off on this side. But if you look at the amplifier graph, it's different than this one because it's getting big on both sides, because that X just makes everything negative and flips it over. So they're very similar graphs, but this one is what's what we call dampening. And dampening functions are very important. You'll get into those a little later in your mathematical career, but we do spend a lot of time with dampening functions in different levels of math in the future. So those are college level maths, but basically, like if you pull a spring and it bounces back and forth, the action on the spring, because eventually it stops bouncing, is called a damper. So this is what that would do. Now here's the one that I was very confused by and remain a little confused by. It got a little better when I looked at it this time. You cannot see it. You can kind of see a couple of little waves here. Here's its peak at 100. And like I kind of showed it, going up past that number after a little while. I really don't want those dots on it, but like there's 0, 0 at 100. And the wave is like when it, because it's got basically your quadratic shape here, because it is kind of a quadratic equation. So if you look at 100 minus x squared is this green graph, and it's following that path very similarly to this one with the 2x, and the sign part here at the end is making it wave. We also changed the period on this, so it's waving a little more quickly, but it follows that sine wave. See how it's down here at 10 and negative 10 are still the intercepts, no matter which one you're talking about, but it's waving a little around that curve. So it's a very interesting thing in my graph, like I said. Not really very accurate. This one was the one I was off by the most. But again, it follows this. I'm going to kind of make this dashed. And so we've got this waving fun. So make sure you get these graphs in, and then we'll talk about the last one. So here we have all of these things. It's great. The last thing it asks us to do in the lesson, so we've got our things, we've talked about what we got right, what we missed, whether we missed a lot. Like the only thing I'd write on this is that it should start at 100 and go up a little bit after that. The rest of it is bizarre what I drew, so compared to the graph. So, that kind of thing. But then the last thing it asks us to do is make up our own equation and propose a different right to the engineers so that they can figure out something else and maybe why it would make a better ride than one of the other ones. So good luck with that, and we'll talk later.